Yes, thank you, Rudy, and thank you, all of you. Thank you very much for this invitation. We're very proud to be here and to present today. My colleague Pablo Pena is going to present. I'm sorry? What was the music?
Sorry, it's off, yeah.
Okay. So I'm glad to be here and to do a very short introduction, but because the main topic of this presentation will be held by my colleague Pablo Pena, that's going to talk about a very interesting topic, that is the transmission expansion with a high percentage of renewable in an electric system. And just to go on with my introduction, let me tell you that we are here. We both work at the University of the Republic, at the Faculty of Engineering. Here we have a very nice picture of our faculty in Montevideo, Uruguay. A glimpse of the offers that our university has, with around 23 careers and more than 8,000 active students and more than 900 teachers in our faculty that has several offers for students for degree and other studies in the topic. But what I wanted to point out here was to give you a short overview of Uruguay, our country, and specifically about the development that in the last year has had our electric system, and how are the challenges that we have faced. That is, one of them is what Pablo is going to address. So Uruguay, as you may know, is a small country in South America, surrounded by two giants like Argentina and Brazil. A small country, we have around 3.5 million inhabitants. And well, this is some of the indexes that characterize our country. It is we have a very low density of inhabitants throughout the country, because most of it we have a lot of space that has allowed us also to develop wind and solar very extensively, among other activities, mostly agricultural activities that we developed in the country. And going specifically, what is the energy framework and the historical background that we have, and that somehow conditionated us for the development of high percentages of renewable, is that Uruguay has no oil, no coal, no natural gas. So far, we have a large tradition in the development of hydroelectricity, but today we can say that we have mostly no space for at least big new hydropower plants. And also, given these conditions, we were very dependent on oil imports, of course, for transportation. That is one of the challenges that still remain in the country, but also to cover for the lack of electricity that we may have from our hydropower plants. In 2008, an energy policy was designed that in 2010 became a state policy, was ratified by a special committee including all political parties. That energy policy was had an adaptation and a ratification in 2020, but like a short overview, it had 4 strategic guidelines. And specifically in the energy supply, it aimed for the diversification of the energy mix, mainly to reduce the proportion of oil imports, increasing domestic resources, and promoting non-traditional renewable energy, specifically biomass, wind, and solar energy. So among that energy policy, it came the development of the renewables like wind and solar power plants. Let me tell you more about the electric sector. That is the topic that we're addressing more in specifically right now. Well, as I said, Uruguay has no oil, no natural gas, and no coal. There are energy resources for electricity generation, or at least traditional. We have almost no space for new large hydropower plants. And just to put you in perspective, because you're going to see figures, and it is important to put that figures in perspective. I said we're a small country, and also we have a small electric system compared with other electric system. Our annual electricity energy consumption is around 8,000 gigawatt hour. We have a very high degree of electrification. 99.9% of the country has electricity. The mean hour power demand is 1.2 megawatts. And the peak power demand that we had last July, that is winter in Uruguay, was 2,290 around megawatts. Just to keep in mind that when we talk about figures, and when you see figures, we're referring to this size of system. So this is the country. This is how the power plants are distributed all over the country. In the south part of the country is the capital, is Montevideo. In the south part of the country is where mostly half of the population is located. So it has the highest consumption of electricity. So traditionally, we have here located all our fossil fuel power plants. And then we have in the middle of the country, here in the light blue line here, we have 3 hydropower plants. And then the biggest hydropower plant is here in the north. We share it with Argentina. It's a shared resource. It's Salto Grande Dam. But also all over the country, we have distributed like the same amount of wind that we have from hydro, like 1.5 gigawatt of wind power plants. We have a big amount also of biomass, like 700 megawatts. And we have 330 megawatts of solar power plants, of course, all again distributed all over the country. Our electric system is highly interconnected with our neighbors. We have a capacity of 570 megawatts of interconnection with Brazil, and we have a capacity of interconnection with Argentina of 2,000 megawatts. Keep in mind that our peak demand is around 2,000 megawatts. So we are very highly interconnected. I would say we're highly interconnected, but not highly integrated, because our systems do not behave like an integrated system. But of course that we rely, and we have relied in our neighbors in times when we were needed of energy. And of course we have given support to them when they need it. As I told you about the energy policy that came in place in 2010, 2008, and 2010, and based on that energy policy, wind and solar power were developed. The biggest development of that sources of energy came in place roughly between 2013 and 2017. Yeah. And then you can see this is how electricity has been generated in Uruguay since 2002. And you can see that before 2015, let's say, whenever we don't have hydro, that is the blue that is in the bottom of the graph, we will have to call for thermal power plants, that's all from oil derivatives. And also we have to have energy imported from Argentina and from Brazil. But then you see that when we started to develop wind, and when it was a mature technology here in Uruguay, whenever we don't have hydropower plants, we no longer have to rely as much in thermal power plants, but we do rely on wind-based electricity, and also from solar, and also from biomass. That has changed how our energy is supplied. And we can say that in many years from now, more than 90% of the electricity in Uruguay has been generated from renewable sources. So that has been something good. It has give us more energy independence from oil importing from oil imported fuels, but also has posed several challenges from the operation of the system and also from the point of view of the planning of the system. As I said, the thermal power plants are located in surrounding the Montevideo area, that is the capital of the country. And before the development of wind and solar power plant, this in the left side of the screen was our electricity generation system. It has thermal power plants in Montevideo, 3 hydropower plants in the middle of the country, and 1 hydropower plant in the north part of the country. Once we developed wind and solar power plants, well, this is the landscape that we have right now, and the landscape that we have to cope when operating the system and also when planning the system, not only the generation system, but also the transmission system. And this has posed many challenges that specifically what refers to the transmission system, Pablo Pena is going to talk to you about this. So Pablo, I leave you, the floor is yours. I'm going to stop sharing.
Thank you, Virginia, for the excellent introduction and for setting the context. And thank you, Rudy, for this opportunity. It's a pleasure to be part of your COIL sessions. In some cases, being a small country is an advantage, and this is clear the case. We all know each other, which foster unique collaboration. For instance, Virginia worked the National Energy Agency, while as was at the utility in the transmission area. But we are also colleagues at the university. As Virginia mentioned, our electrical system serves as a toy example, being so small, making it extremely useful for example, for testing algorithms or to test new methodologies, as I will show you. Paradigm shift in transmission expansion planning. Historically, power generation in our network, as Virginia said, was concentrated at very few nodes, and the grid was minimal meshed, resulting in well-defined flow patterns, either thermal or hydraulic, coupled with winter or summer peaks demands. This simplicity allowed to analyze and design the transmission network based on small pool of worst-case scenarios, which is typical in transmission system analysis. However, the widespread integration of wind and solar power has fundamentally altered this landscape. These renewable sources are now connected across the entire country, significantly diversifying our traditional flow patterns. Additionally, with the grid becoming more meshed, the complexity of flow patterns has increased, presenting new challenges that have led to a paradigm shift in how we analyze the network performance. We move from a deterministic methodology, which focuses on worst-case scenarios, to a probabilistic approach using the Monte Carlo method, sequential Monte Carlo. This new approach allows us to analyze the diversity of load flow patterns. By using the repeat random sampling, we simulate the optimal dispatch for the future study year, taking into account rainfall, wind, irradiance, and demand curves, hour by hour. This generates almost 1 million scenarios for 1 year, represented here as vectors, where G is the power injected by each generator, and L the demand consumed by each load. By solving the load flow for each of these million scenarios, we obtain a Monte Carlo analysis of the network. The challenge is that resolving these million scenarios by an iterative method like Newton-Raphson is time consuming, and this process must be repeated for each contingency. So we decide to group the scenarios into clusters and solve only a few representative ones. The key question is how to group these scenarios. Typically, scenarios are classified based on the contribution of each generation source: high wind, high solar, low solar, combined with demand levels, peak, valley. However, this may not be representative of the power flow in the network. So we apply a linear transformation based on the power transfer distribution factors, PTDF, which allow us to obtain the DC flow for each scenario. This PTDF-based method is a cold start type, meaning the PTDF matrix depends only on topology and not on the Jacobian or it's just an algebraic calculation to solve scenarios, and it is really very fast. This is a toy example with 16 scenarios and 2 lines. Sorry that it's in Spanish, but it represents the power flow in percentage of the rate in each line, and the DC power flow in each line. And each cluster represents a power flow pattern, and a representative scenario is determined for each one. The probability of each representative scenario is assigned based on the size of the cluster. The bigger is the most probable, and the yellow cluster are the less probable, but in this toy example are the worst case. By solving the AC power flow of the representative scenarios, we obtain this type of results for each branch, for each line, underground cable, transformers. This methodology not only helps us to predict the maximum expected flow across each branch of the network, but also assess the probability of potential overloads. Being able to estimate this probability, we have established new criteria for evaluating overloads, which could enable us to enhance line capacity by as much as 25%, while the likelihood of overload remains minimal, and we have a safety margin. More recently, we investigated the application of 3 alternative methods that proved to be very promising, and which I will discuss without going too much into what's under the hood. You can find more details in the paper we presented last year at the SIGRE Ibero-American Congress. It's in Spanish, but feel free to contact me for further details. We tested fully connected neural network to estimate AC power flow and replace iterative method like all supervised learning method requires training data. So it's necessary to solve some AC power flows using traditional methods to train the neural network. The results were very good, and computational times were reduced by an order of magnitude, including the training time. However, this type of neural networks that is fully connected, deep learning, is trained specifically for each topology, requiring retraining for every contingency you would like to analyze. I suppose that in a new future, with the advancement of graph neural network, it will be possible to have a single neural network that can generalize to different topologies. We are working on that. The other two methods do not use Monte Carlo approach, are analytical method for probabilistic power flow. And the idea is to determine the moments or cumulants of the input variables, and from them obtain results that allow the reconstruction of the probability density function of the output variables using, for example, Cornish-Fisher or Graham-Charlier series for the reconstruction. The point estimation method uses any traditional load flow solver. We in Uruguay use the PSSE of Siemens. And the idea is to solve a kind of scenario by combining different input moments. It requires to solve only, for the case of Uruguay, only 3,000 AC power flows. And it's the fastest, taking only 100 seconds per topology. And finally, from my point of view, the most interesting and promising is the holomorphic embedding load flow, multidimensional holomorphic embedding load flow. And it's a relative new approach that embeds power flow equation into holomorphic function, expressing solution as multidimensional polynomials of complex variables. This method provides higher order approximation beyond linear models and accurately estimate voltage and power flows, active, reactive powers. The great advantage of this method is that it does not require an iterative process. Some personal information. I was born in Montevideo, in Uruguay. I come from a family deeply rooted in the science. My mother was a mathematics teacher, and my father is an industrial engineer. And I'm electrical engineer of the Universidad de la República. I have three brothers. One is a chemical engineer, another is an industrial engineer, and the youngest is not an engineer, has a venture into sociology. I hold a master's degree in the integration of renewable energy into the electrical system from the University of the Basque Country in Spain. And it was there in Spain that I met my wife, Claudia, who is a chemical engineer and a researcher in the Universidad de la República in the School of Engineering. Together, we have two wonderful children, Martin, who is 9, and Cecilia, who is 3 years old. Professional, I'm deeply involved in Uruguay's energy sector. I lead the transmission network planning and design team at UTE, that is the national utility company. And additionally, I serve as part-time professor at the School of Engineering, training the utility experience and sharing different projects with the undergraduate and graduate students. So let's move to a more real and less model and simulation topics. But first of all, I'd like to introduce the topic of dynamic line rating by the basic of line rates. The temperature of a conductor in a transmission line depends on several factors, including heating effects like Joule heating and solar heating, as well as cooling effects such as radiative cooling and convective cooling. Traditionally, system operators have used a static rating for transmission line based on extreme local weather conditions. For example, the static winter rating for this line with a How conductor in Uruguay, calculated under the assumption of low wind, typical 0.6 meter per second, maximum irradiance, that in Uruguay is 1,100 watts per square meter, and the highest ambient winter temperature in Uruguay. So the ampacity or the capacity is 370 amperes. In this way, the operator defines a maximum current that ensures a safe maximum conductor temperature, one that neither damages the conductor nor compromise the ground clearance distance, regardless of environmental condition. However, the reality is that winter temperatures are often below 30 degrees. I refer to Celsius degree, and irradiance is lower, especially at night, and wind speeds are usually higher than 0.6 meter per second. As a result, much of the time there is an extra capacity that isn't being utilized. And this is what dynamic line rating seeks to capture. Wind is the most sensitive variable, so if instead of considering low wind, we use wind speed of, for example, 10 meters per second, the line rate will increase by a factor of 3, as in the example. Now, let's shift to the real world experience. Since 2015, we've been operating 2 lines with dynamic line rating sensors in a pilot project, along with trial of sensorless solution and the installation of 14 weather stations, and tested a dynamic line rating system based on this data, the weather data. Furthermore, we have adapted dynamic line rating as a solution for the transmission expansion planning and for connecting new projects. For example, the new Google data center that will be in service in few years. Now, let's look at some results of this experience. This violin plot showed the performance of 4 different dynamic line rating systems over a full year, separated by winter and summer. In blue, we have the system based on physical sensor attached to the conductor. The green represents a system using weather station, while the orange and the red represent 2 sensorless systems. All systems reported ampacity above static for at least 80% of the time. Additionally, dynamic line rating exceeded the the static thermal rating by more than 30% for 20% to 60% of the time, depending on the system you select. But okay, these results are statistical. What's happening in real time? How do the system compare when faced with actual dynamic conditions? And the reality is more challenging, especially for sensorless systems that rely on models to estimate the environmental variables along the line. And in this example, over a 48-hour period, the sensorless system overestimated the line's capacity, and for nearly half a day, they estimated double the actual capacity. Well, for more details on this comparison, you can refer to the paper we presented at SIGRE last year. So the question is what? Why? What failed? Critical spans where wind is blocked are the major challenge for dynamic line rating from my point of view, as they can affect the line performance. Uruguay's terrain, defined by gently rolling hills and no mountains, seems perfect for dynamic line rating. However, we have extensive eucalyptus forests, as in the picture, that act as barriers and reducing the wind flow and consequently the cooling effect on the line. With eucalyptus trees reaching height of 20 to 25 meters and taking into account that the conductor is at 7 to 15 meters high, this forest corridor can severely impact the efficiency of dynamic line rating by limiting the cooling provided by the wind. So we conducted computational fluid dynamics simulation and installed a meteorological station within the forest corridor to understand this phenomenon. This effort confirmed that wind speed within this forest corridor is nearly zero and aligns parallel to the transmission line, which means there is minimal cooling. Based on this finding, last year, the Uruguayan transmission system operator, UTE, adopted the ambient adjusted rates as a first step in the adoption of dynamic line rating. This approach, while conservative in wind speed estimation, allow for increased capacity utilization, especially during winter and nighttime when cooling demands are lower. This heat map is really interesting. It was created by my students for their undergraduate final project and represent the adjusted ambient rates by month and hour, based on 10 years worth time series. And as expected, the lowest rates occur at midday and during the summer. Remember that here for us summer is in December and in January. So in this area you have the lowest rates in these times. So bad news for system looking to expand solar generation, as the correlation does not work in their favor. Each degree counts. this could be the slogan for my tattoo, because every details matter, and we work in that direction. Our lines were designed with a clearance of 7 meters, while the next code is the code we use, the United States code that we use here in Uruguay as a reference, requires a minimum of 6.5 meters. That leaves us with a possible margin of 60 centimeters, enough to allow for an extra degrees, which translate to extra capacity. However, some of our lines are over 60 years old, and due to the effects of creep, ground movements, and the lack of GPS at the time, the planning altimetry is not very precise nowadays. So we are creating a digital twin for our overhead lines using LiDAR laser technology, covering the first 1,500 kilometers. Is the third part of the high voltage network. And this precise model will enable us to accurately determine the maximum conductor temperature for each span and identify specific limiting spans. Once we have this information, we will define the uprating actions for each case. Conductor retentioning, ground movements, isolated cross-arm, or high temperature, low sag conductors, for example. This action will enhance the grid capacity with minimal environmental impact. Another problem we face in the grid is the congestion in the 150 kilovolt grid, where both the generation and the demand are primarily connected, and which leads to congestion in the high voltage grid. However, the extra high voltage system has 10 times the capacity of the high voltage network. There are some promising solutions for reducing congestion. They are called the grid enhancing technologies, the GETs. One is the use of series static synchronous compensator. The idea is to use a fact in series with the line to add a voltage in phase with the current, acting as a series capacitor or a reactor to push or pull the power flow in the lines. And we have evaluated this technology in 2 locations, in north and in the east. And while the solution effectively resolved the congestion, it wasn't economically attractive, and in these specific cases, maybe it seems like an excellent solution for urban areas with environmental constraint, or for rapid deployment. But in this case, there are other alternatives. And another promising solution is the grid topology optimization, but by making topology change at the high voltage level, we can alleviate some of the congestion, switching line off. But there is always a but. Nowadays, the 150 kilovolt grid also serve in Uruguay, serve as a backup for contingencies in the 500 kilovolt system. So in our case, meshing the grid, the extreme high voltage grid network is crucial to enable this option of power flow redirection. Additionally, there is a need for grid topology optimization software development, not only for real time, but also for expansion planning purpose. Imagine to mix the 1 million scenarios and now change repeated for each contingency and for each topology change is a challenge. So some takes away and conclusions. Planning the network requires innovative solutions with renewable generation being stochastic. For example, the method I mentioned before. Rethinking how we analyze the grid could be the easiest and most cost-effective way to integrate more renewables. That's what's happening in the Uruguayan system at the beginning of the transition, by changing the worst case scenario to a probabilistic approach. Dynamic line rating can increase capacity. It's a fact. It's the truth, but requires sensors, physical sensors, at least in critical spans or weather stations in those cases. And ambient adjusted rates and dynamic line rates too has negative correlation for solar generation integration. So take it into account if you pretend to span your system with solar generation. Be conservative when uncertainty is inherent in the problem, but take advantage of design margin if you can increase the precision, for example, using LIDAR and a digital twin. And finally, power flow control or GTO to alleviate high voltage grid congestion. It's a good idea by redirecting flow to extra high voltage grid, for example, as the case of Uruguay. But depending of the case, you may need some new infrastructure, new lines, or mesh the grid. So this has been a summary of what has been happening in the electrical system of Uruguay, let's say in the last 10 years. Well, thank you very much for your time and attention.
Well, thank you, Pablo and Virginia. Excellent presentation. So if you stop sharing, I can see. All right, very good. So I want to open the floor for questions to Pablo or to Virginia from the students in the digital virtual classroom. And as I mentioned at the beginning of the talk, there are some students from the University of the Republic of Uruguay. So please, you're invited to ask questions of the speakers. So students, please introduce yourself, unmute yourself, and introduce yourself, and then ask a question, please. Sajjad, please unmute yourself.
Hi, my name is Sajjad Al-Shammari. I'm a student for Master in ESE. I have a question about the overpower. What will do when you have renewable energy, when you have overpower generation? And the second question about the sea turbine. I see don't have the sea turbine. This is the second question. Thank you.
First question.
Thank you. Very interesting questions. I would like if you can clarify when you refer to overpower, you mean overloads or more generation than demands power?
More generation. If you have more generation unwanted.
We are, as Virginia showed, we have two strong interconnection in comparison with our scale, one with Brazil and the other with Argentina. In some cases, we export the exceeding power to Argentina or Brazil. Of course, sometimes the business is not so interesting, but maybe Virginia has more details about that. And the other, and sometimes we, of course, we have to maintain the frequency, so we have to cut some renewable sources. But we have a big lake associated with in the middle of the country, associated with an hydroelectric power, so act as a storage, and so we can save water if we have enough renewable like wind and solar, and then use during the night the saved water. And the other question was sea turbine.
Sajjad, what is your second question, please?
Just only about the sea turbine. They are facing to the ocean because they can put some turbine on the ocean.
I know some experience when I was in the Basque Country, but we are in Uruguay. As far as I know, we are not testing those kind of generation, and we are not we have no offshore wind generator or sea generator right now. I don't know, Virginia, if you have other idea.
No, have that kind of technology, and for the first question, it's just like Pablo said, we take advantage that our generation system is quite flexible because we have the hydropower plants and we have a space to store energy in the lakes, and we try to use them to follow the variability of wind and solar power plants when we can. Sometimes we can arrange to export energy, and when that can't be done and we don't have enough space, we have to curtail the wind and solar.
Thank you.
Okay, thank you. Questions from students? Please unmute yourself and introduce yourself and ask the question, please. Okay, I'm going to open it up to general audience. Questions from general audience? Hamza, go ahead. Oh, sorry.
Hi, everybody. First of all, thank you all so much for the presentation. I just love listening about Uruguay's energy transition. I have a question. My question is that in the past few years, Uruguay has achieved a lot in the field of renewable energy and technology development. But what is the next big challenge or the next big goal of the country that you guys are planning or at least trying to achieve in the next decade or so in terms of renewable energy?
Virginia, I think you are the the excellent person to answer.
Yeah, I mean, when we looked into the future, we see that renewables is still the answer for continued development. We still have a very huge challenge because, as I shown, we were very dependent on oil imports, and we have diminished dramatically the oil imports for the electricity generation, but we still have to work in the other use that we have for oil derivatives in the country. So the next challenge is reduced oil imports in transportation, and the country is just working on that with the development of electric vehicles. And also the next big thing that we have ahead of us is the development of hydrogen to use in some cases when it's hard to abate the consumption of oil derivatives. Uruguay has in place a strategic guideline for green hydrogen. We're in a very good position because, as we have shown you, our electric system is considered green, so we will be able to develop green hydrogen. It is something that is required for of course to continue with respecting and improving our environment. So that would be the next challenges that we have ahead of us.
Perfect. Thank you very much for that. I appreciate that. I do have a follow-up question. Is Uruguay looking into developing the nuclear sectors, basically nuclear power generation?
Nuclear energy is for now forbidden in Uruguay by law. So we are not considering it right now. It has been considered in the past, but it turned out to be more, I think, logical, the development of renewables and the huge potential that we still have. I think that it is something to be considered before every other technology like nuclear. But this is perhaps my personal point of view. And I talked about the regulatory framework. It is forbidden by law, nuclear power in Uruguay. And also I think that we have potential for other sources before considering that option.
Thank you very much for that. I appreciate it very much.
If Alberto, you had a question? Yeah.
Yes, so Pablo and Virginia, thank you so much for the presentation. I had a question regarding the way that you assess some of the benefits and costs of the measures. So for example, when you're doing dynamic line rating, you need to do a lot of capital investments, right? Which are one-offs. You're in a system that is mostly renewable, so marginal cost is basically zero in many cases. Like you may have some hours in which it's not, right? But it's very low. How do you compare those two things, right? So could you compare capital cost of one versus the capital cost of the other, or how do you assess whether this is a good investment to do or not?
Good.
Up to now, we have been using dynamic line ratings as an invest and pay the license per year in pilot experience. And now who lead the use of dynamic line ratings, for example, as I mentioned in the Google project, is to enable the connection and to not to build new overhead lines that will be needed if we don't use dynamic line ratings. So, but your question, it's very relevant because nowadays the TSO is not a monopoly in Uruguay, the transmission market, but there are only one, the public transmission operator. So we are working in introducing this kind of technologies that has a cost, but in the future they should be included in the toll, in the pay that the market do to the transmission. We work with the benefit of the whole country in mind, but has some business problem that we have to solve in the regulatory with new regulation of that kind of technologies that now we are not paid for.
Okay. Thank you so much.
Okay. There's a question in the chat line from Joe Andersoni. Can you discuss consumer cost of electricity as you have utilized more renewables? Has the cost gone up for cost of electricity since you made this big change? No?
It's a hot topic, Virginia.
No, but I would say is that what renewables have gave us is we don't expect, we are not subject to external variations in the cost of electricity as we were in the past. In the past, we were very dependent on the price of oil, and sometimes the tariffs will have to be raised more than once in a year if the oil price goes very high and we have a high low hydroelectricity. So the cost for the supply of energy would be much high and the tariffs will go up. So I think that one thing that renewables have gave us is that we don't expect as much variation in the cost for supplying the demand. It's something that it has very positive aspect of this. Of course, there will be many things that should be improved in the future in order for the development of the contracts of renewals. We have learned a lot, I think, about how to reflect the price in a contract to be more convenient for the utility, something that has to be worked out. But I don't believe that renewables have made prices go up, but made them more stable. And if you think in the development of the tariffs of the last periods, I think that you can see that it eventually gone down in present terms. I think I don't know, Pablo, if you want to add something about this, but like an overall conclusion is, I think that they have helped to not to raise that much the tariffs, and also to help maintain the cost of supply of energy supply.
Yeah, and I agree. I agree. And we have to take into account that the transition in our matrix was more than 10 years ago. The contracts are more than 10 years ago, and so the price in the contract is still in dollars. So maybe in a future, I suppose the new expansion we will access to lower tariff, or maybe in to access to energy in the spot, that nowadays is not the case.
Questions from the audience for Virginia and Pablo? Let me ask a question, Virginia and Pablo. The Uruguayan grid is almost 90+% or more renewables. And, I know it's a small country. And so we have to compare it with the US, which is a very large grid. But we rely on still, thermal processes to produce electricity. And we rely, the thermal, with the majority of the plants being thermally driven, we rely on spinning reserves, for inertia, grid stability, and so on. And so how do you made such a big change as far as grid stability is concerned? Is it any better or is it worse than before, or how can you comment on that? As far as availability, as far as reliability?
We are strong. We have a different frequency with Brazil, that is 60 hertz, and in Uruguay we have 50, and the same as Argentina. We have a too strong connection with the Argentina system. So in terms of frequency stability, for good and for bad, we rely on Argentina.
Okay.
This is the situation right now, but your point is it's a key point to solve in a future where the hydropower in Uruguay be less representative than in respect to the other renewable energies. But I hope that grid forming technologies in the future will change the idea we have right now about solar and wind generator.
Good. Okay. There's another question on the chat line. Do you take rainfall into account in limiting current on transmission lines? For example, if it's a very dry season, forest fires are high risk, must you derate the current flow?
Yes, there are two very interesting points. The first question, no, we don't take into account rainfall in the line rating. And there is an idea, but nowadays we are focused on we lack of some information, and after we have the digital twin of the overhead line, we pretend to take into account the high risk seasons for fire and the rate current if it is needed, because in Uruguay we have wildfire problems in wildfire, and we don't want to be the responsible for that. So after the digital twin, that's give us not only the towers and the conductor information, if not the vegetation in the right of way, will be taken into account.
Yeah. Any questions from the audience? So Pablo, a question for you. Your transmission planning is also, very novel and obviously very new to most of the other grids. You're looking at probabilistic flow models. You're not looking at deterministic models. Have you kind of shown that you save a lot of money if you were to you're following something which is very new, but you're also cutting back on costs. You don't have to take on big capital projects to change out. So, and did you do a financial analysis to see that savings you got, or?
I once we change, we didn't go back to analyzing in a worst case scenarios.
Yeah.
But most important than save money, I think is to I save my health because if you continue using the worst case scenarios and you combine full power in a scenario, you put full solar generation and combine with the valley, the demand valley, the minimum demand that's occurred in the night, in early in the morning at 4 a.m. in Uruguay. So this is not real. But in the middle, if you consider peak summer demand and full solar generator, you have a widespread of scenarios. So which is the point which you select? At the beginning, we started by using, wind is not correlation, is not so perfect correlated. Even being small Uruguay, you may have full wind in the north and zero wind in the south. So which probability? And we started to define different scenarios in the business as usual, trying to add more and more worst case scenarios, or not so worst, but middle case scenarios. And at the end, we say, okay, what are we doing? Which is the probability? And maybe you can combine the full solar with the minimum demand value. But what happened on Sunday? Maybe Sunday at the middle day in Uruguay, which is well, you may have not in summer, but in autumn or in spring, you may have low demand values. So it's an interesting question. We didn't went back to to analyze the worst case scenarios. We still use it for some specific cases in terms of voltage collapse or some stability problem, but not for overload. We still use worst case scenarios, but specific for voltage analysis, not for overload.
Yeah, the reason I asked the question is that, just a recent case, Duke Energy here, they kind of adopted some of the techniques you followed to interconnect like 2 gigawatts of solar energy, and they saved like 70% cost. So, it was quite prominent, as to how proper planning, looking at probabilistic methods, was very important. So anyway, there was a recent case study on that, and so I just wanted to kind of see if you had something similar to that you guys did. Questions from the audience? You have a question that you want to voice, and you put it in the chat box. Okay, hearing no questions, going once. Well, thanks a lot, Pablo. and Virginia had to leave because she had another meeting. But thank you for your presentation. And we'll have our next seminars 2 weeks from now. And we're continuing to look at energy transition experiences throughout the globe. 2 weeks from today, we'll have a speaker from University of California at Berkeley talking about the energy transition in India. So, India, of course, is a rising power. They have the third largest grid in the world, but they use a lot of thermal processes to generate electricity. So that experience probably will be very different from what you just heard today. Thank you again, and look forward to seeing you in a couple of weeks.
Thank you, Rudy, and the audience, and have a good day.
Okay, bye-bye.